I'm Roy Rappaport.
And I'm Chris Sandin.
We're here to talk about real-time analytics and how you can use them to make better self-healing ecosystems. So let's start with maybe introductions. I've been at Netflix for a little more than 6 years. I actually joined back when we had an IT group responsible for a whole bunch of data center systems. So I remember those days not particularly fondly. These days I work in a group called Insight Engineering. We are a software development group, part of Josh Evans's operations engineering group, if you attended his talk, responsible for real-time operational insight systems.
And I am Chris Sandin. I'm a senior analytics engineer on the real-time analytics team, which is part of Roy's Insight Engineering team.
So
I've been at Netflix for roughly 2.5 years.
So hi. Okay, good. So to start this off, to set it up, I want to talk a little about the prerequisites for getting value out of this talk. So let's start with this. Who here has a PhD? Actually, maybe let's go as low as a master's in machine learning. Raise your hands. Okay, so you might be bored by this presentation, and it's okay if you leave right now. Everybody else, you're in the right room. So our goal here is to go over some algorithms that people like, well, people more like me, I guess, than Chris, people who are responsible for operational systems can use to build self-healing ecosystems. So we're going to talk a little about data science. We'll talk a little about algorithms. But the real goal here is to expose you to enough to actually be able to play with this and start experimenting in your own space. And the way experimenting with this ends up looking like, I think, is I think for most of us who have what I might think of as reasonable telemetry platforms, you have this telemetry platform. I use a heart both because I love telemetry platforms, by the way, but also because this is sort of like the heartbeat of your environment. And you probably have some sort of orchestration system. And I'm saying that because, frankly, most of the people here, I'm guessing, either are working in the cloud or are looking to work in the cloud. And at minimum, you have the AWS API. And so the nice thing is, even if your telemetry platform doesn't have real-time analytics built into it, and don't feel bad, ours doesn't either, given the information that we're going to give you today, you can go away and start thinking really as an RTA system that is standalone, and then can basically get information from your telemetry platform, assuming your telemetry platform has API access to the data it holds. Otherwise, I would argue it's not particularly reasonable. And then the RTA platform can make decisions based on that data, drive those decisions into your orchestration systems, which can then make your environment change for the better, hopefully. And that actually drives better observation, and you've got this virtuous cycle of data, decision, and observation. So that's the way we're hoping you can use the information we'll talk about today. So why is this a good thing? Well, I want to talk a little about bad news. When I moved over from the IT side to engineering at Netflix back in 2011, and we were starting to figure out how do we know when there's a problem with the website, it started with basically, we'll just be told about it. So, it started with, in 2011, our customers are the best source of information we have for whether or not we have a problem, which is a great way to start, but it's kind of embarrassing because ideally, we'd like to notice that there are problems before our customers do, and ideally, maybe even fix them before our customers do. So everybody starts with, gosh, it's embarrassing when our customers tell us that there's a problem. We should figure this out by ourselves. So the next step is you go with dashboards, and everybody loves dashboards. Dashboards, I'm convinced, are responsible for some of the biggest explosions in sales of large TVs in the industry because everybody ends up putting them all over the walls. Here, you actually see two of the most important graphs probably at Netflix. The top one is calls into our customer center, basically minute over minute. This is a 7-day cycle. Black is last week, red is this week. The reason this is important is because we don't actually sell anything over the phone. And that means that chances are when people call us, it's not to tell us that we're doing a great job. Chances are when they're calling us, it's probably related to the bottom graph, which we call SPS, or starts per second, which is actually the number of times people hit play on their remotes to start watching something on Netflix. Again, black is last week, red is this week. SPS, by the way, is the metric we use to define availability. So when we look at how good our availability was for a given week, we basically look at the difference between what we expected SPS would be and what SPS was, and look at that as essentially the downtime. one way to think about that is that essentially we measure our downtime in customer disappointments, which makes this, I think, super relevant for us and kind of painful, which is the way you should be thinking about your downtime. So you've got graphs, and that's great, and you may even hire some people whose only purpose in life is to watch graphs and watch when they go wrong so they can start hitting the big red button and get people notified. But that's a miserable existence, and there's just too many graphs to look at. So the next obvious step is, alerting. I'm sure all of us have gotten this kind of alert before. And that's where a lot of us stay for a while. And we stay here because, to be perfectly honest, this is not a bad place to be. You've got some visualization, you've got some alerting, and frankly, this is a pretty necessary way to deal with the world. It works pretty reasonably well, but it's not particularly sufficient as you grow larger or more complex. And then what happens? Well, as it turns out, for us especially, as we get bigger, we end up with a whole bunch of kind of interesting problems. And what we end up with is essentially complexity, but not just complexity in one dimension, but a whole bunch of different dimensions. And I want to talk a little about those dimensions. And I'm just going to throw some numbers at you. 421,010. We have a system that actually logs every change in production that we make. And I looked in preparation for this talk at the number of changes we made in one of our production regions over a week. This was the number of changes. To put it in perspective, for people who haven't yet done the math in their heads, it's about one production change every 1.1, 1.2 seconds. At that rate, it's hard to keep track of what your environment should look like and what it looks like when it performs well. The other interesting problem that we have is that our telemetry volume is kind of silly, and you can ask every engineer in my team who's working on telemetry platform and all the conversations. Has anybody here, by the way, attended Andrew Park's presentation about cloud efficiency and cost? Yeah, so I'm one of the problems that Andrew has because my product costs a ton of money for Netflix. And when I say our telemetry volume is silly, let me put this in perspective. In US East 1, which is one of our production regions, we've seen upwards of about 2 billion different metrics being reported every minute. 2 billion is a lot. 2 billion is really hard to visualize. So I'd like to actually change from 2 billion, which is kind of a large number, to something that is a little more sort of, think of it as a unit of measure that is a little more relevant and intuitive to all of us. This is a kitten. The average kitten is 14 inches long. I bet you didn't think we'd talk about this. So if every one of our metrics was a kitten, and we had 2 billion 14-inch kittens, what could we do with this? Well, one thing we could do is we could actually put them back to back and form a line from the Earth to the moon, and then back. Now, before you go trying this at home, because we're hoping this is applicable to most people, I should know that if you're going to do that, I urge you to actually equip your kittens with laser pointers that work. Let's see this. Perfect. Good. So it's cold in outer space. Put them in spacesuits. The good news is, by the way, this is the AWS conference. Amazon can help you with that as well. So another thing that happens at large scale is that you end up with really interesting failure modes. And to do that, I want to talk about the Netflix outage that, for me at least, was the most memorable outage in the third quarter of this year. You've probably not heard about this before. So, has anybody here seen House of Cards? Great, fantastic, one of my favorite shows. So, June 4th, 2015, we released a small bit of software to production that was supposed to not have any adverse impact on anybody. Anybody ever done that? The good news is we didn't actually completely break anybody. All that happened was, well, one device out of about 1,000 different device types. By the way, the numbers here are, for me, estimates. They're just orders of magnitude. So one device out of 1,000 device types in one test cell out of about 10 test cells, in one test out of about 10,000 tests, couldn't view season 3, episode 1 of House of Cards. And this went on for a week, and we didn't even catch it. The only reason we found this, to be honest, is that we released something else a week later, and somebody was looking at some graphs and noticed that there was some sort of weird deviation, and then we jumped on this and found the problem. And keep this in mind, right? We had billions of successful streams that week. The amount of disappointments that we generated out of this was vanishingly small. I actually did the math in preparing for this presentation. It was something like 5. We disappointed either 5 customers once, or one really pissed off customer 5 times. And this is a really hard thing to, frankly, catch. In fact, when I was talking to some people at work, I got this great quote from one of our UI engineering directors who said, "We have weird device-specific problems all the time, and interactions with A/B tests only make them more complicated. So I'm not sure we have a pat moral of the story, other than we really like alerting and fast responses." So what makes the cloud interesting? Well, I have some bad news about this, right? When I joined Netflix in the data center, we were running our databases on one huge monolithic piece of hardware from our favorite hardware vendor, who shall remain nameless. And every year or 18 months, we would start noticing slowdowns because we were exceeding the capacity of the server. We would take a few days or weeks to figure out what we needed to get. We would place the order for the next big piece of hardware that cost millions of dollars. They would take some weeks to produce this thing and days to ship it, and then we would take a week or two to build it into the data center and provision and configure and then do the database migration, and it would take like 2 or 3 months. And the good news is that when it takes you 2 or 3 months to remedy this kind of problem, then you frankly have more time to notice it. So let's look at the new world. We use DynamoDB. I have occasionally actually found that I need more capacity from DynamoDB, in which case all you need to do is do an API call to ask for more read or write capacity. And in my original version of the presentation, I was going to say that in my experience, it's taken seconds for that capacity to be provisioned. Amazon actually asked me to say it could take minutes, so as to not overpromise. But still, minutes is pretty darn good. And the thing is, if it takes minutes for Amazon to fix stuff, then you can't take days to notice the problem. That essentially means that Amazon has the potential to make us look bad because they react really, really quickly. Now, there's some good news too. It turns out that infrastructure is no longer the bottleneck, and that things that took weeks before to change now just take an API call. And by the way, I love slide reuse. And that also means that you can do a lot of rapid recovery, and you can do automated response, because everything essentially is one API call away, which if you are a lazy person, as I am, and as most of the engineers that we've hired are, then Amazon potentially allows you to do a lot less boring work. So how does this end up working for your advantage? That's Chris's part, but before Chris gets into his part, I want to talk a little about some of the capabilities that you probably want to have in your environment in order to be able to take advantage of the algorithms that we talked about. The first thing is time series. So you probably should have some sort of monitoring system that allows you to create some sort of monitoring time series for some sort of metric. That's pretty elementary. It's also nice to have some sort of event streaming system, whether it's based on Elk or Spark Streaming or anything else. And if you're running in a service-oriented architecture, automatically discovering dependencies and looking at the relationships is kind of a nice thing. And on that note, Chris, would you like this non-functional pointer?
I would love it.
Yeah, it's not functioning. Oh, it kind of is.
It does work. That's a tough lead up to follow, Roy. So I want to take some time and talk to you about 3 different broad categories of analytics that we have found useful to address some of these challenges that Roy has laid out. Namely, I'm going to talk about prediction, I'm going to talk about detection, and also the concepts of correlation. So let's dive in. So the first category, prediction. Prediction is something we should all be relatively familiar with, whether you've read the historic works of Nostradamus, or you're trying to figure out if the blackjack table out in the lobby is in your benefit. So we want to be able to leverage this power of prediction to be able to make some informed decisions about our environment. And so one of those cases, or one use case we can think about, is the use of predictions for predictive scaling. Now, who here is familiar with autoscaling? All right, a good part of us. So at its core, autoscaling is a reactive model. For example, let's take a look at this example autoscaling policy. So we want to scale up our service here by 10%. And we're going to do that when some workload, in this case, for example, requests per second, breach some threshold. So by nature, we are reacting to something in our environment. So we're reacting to when our requests per second exceed some threshold. This has been a big win for a lot of companies, big and small. But there are a set of advanced use cases that reactive autoscaling doesn't handle. For example, one of those use cases is where a service may have rapid, reoccurring spikes in demand. So for example, let's say you have a service that every Monday at 4 o'clock sees a big increase in traffic. And let's say, for example's sake, that your service takes 40 minutes to start up. In this case, every Monday, you may be under-provisioned to handle this load. Another case where reactive may not handle well is where we have variable traffic patterns. For example, the traffic pattern on a Monday, Tuesday, Wednesday, or Thursday are all going to be slightly different. And third, and maybe more importantly, outages. As Roy noted, we all do push code sometimes that can cause outages. So in this case, if we were using reactive autoscaling, you push a new piece of your software, and there's a bug in it, and your requests per second come down, and that's what you're using to scale. Reactive autoscaling may start to scale your service down. And when inevitably the retry storm comes, when your service becomes available, you're going to be under-provisioned. So these are some use cases where we can apply predictive scaling or predictive analytics. So at the core concept is that we want to anticipate change in our traffics and our workload. From that, we want to make some predictions. We want to predict the resources we'll need ahead of time. And finally, we want to proactively scale up or scale down our services. But before we can actually talk about the algorithms or the techniques, we need to pick the right metrics. We need to pick the right data. So we need to have a clear, relatively stable, and reoccurring pattern to our data. It's very hard to make a prediction on noisy, random data. Furthermore, we want our metric to be independent of any type of cluster performance, as we'll see shortly. So for these reasons, we use a metric called requests per second, or RPS. So we can see that this metric exhibits those criteria. We have a reoccurring pattern. For example, our weekly periodicities have the same day of week. So our Monday traffic is going to look like Monday traffic. Our Tuesday traffic is going to look like Tuesday traffic. Furthermore, requests per second for us is independent of cluster performance. It is just measuring the total number of requests coming into our service. So if we decide to change the underlying instance type or make a performance change, that doesn't affect our predictive autoscaling. So how can we actually use a metric like this to predict the future? Well, there's a breadth of techniques we can use out there from the world of statistics and predictions. But one technique we have found to be extremely useful is by applying a concept called the fast Fourier transformation, or FFT for short. This is a technique that comes from the digital signal processing domain, and it has some nice advantages. And we've demonstrated or tried to illustrate one here. So imagine at the bottom of this graph, we have our input metric. This is our requests per second. This is a complex waveform. It's made up of multiple things. When we pass this through our FFT algorithm, we can recover or decompose this input signal into a set of simpler sine waves or components. And that's what these top three represent here. So the way we want to use this to do predictions is we want to make sure we maintain our periodicities in our data, make sure we have the same trends and the same cycles. But we want to remove the noise. We want to remove that noise from our signal. And so to do that, it's quite simple. We can decompose our input metric into these set of components, and we can remove the high-frequency components. And these high-frequency components represent the noise in our metrics. So in this example, it might be the top component, which is high-frequency noise. What we can do then is exclude that and use the middle two components, so the second and the third, add them back together, and we get a new signal. And this new signal is going to be smoother than the input signal, and we can use this for prediction. So let's look at an example. So So here's an example where we have an input metric, requests per second, and it's kind of noisy. We can see we have a spike in the middle there. We can also see we have some variability in the underlying data. And we want to remove that. We want to be able to use this to make a prediction. So what we do is we run it through the fast Fourier transform, and out comes the green line. And we see it has the same shape, trend, and periodicity as the input, but it's clean, it's smoother. But to use this, we need to convert it into some type of action. So it's one thing to predict in the future your workload or your metric, but it's one thing to turn that into action. So in this case, we see on the left here our prediction. And we're predicting our workload into the future for a certain service. And this is RPS, requests per second. And on the right-hand side, we see a generated action plan. This action plan says that at any given minute, the number of instances or servers we need as predicted by our prediction function. So the important thing to take away from this is that our action plan matches in shape and kind of curve to our prediction. So how do we do this in reality? So this is a simplified kind of workflow, but we take our metric we're interested in observing, for example, requests per second, run it through our FFT-based prediction algorithm, then we compute that action plan. And that action plan is what we use to talk to the AWS API to say, we need more capacity, we need less capacity. And remember, this is all proactively. However, we can't rely purely on predictive scaling. If you remember, we were removing the noise from our signal. Now that noise represents true workload in our environment. So we have to create a hybrid approach. So we're going to use both the benefits of reactive and predictive together. So in this case, we're going to predict our workload for an application and proactively scale it. But at the same time, we're going to use the reactive auto-scaling to handle our unexpected surges in work. So this demonstrates a great example where we can use prediction to help make our environment healthier or more robust to change. Another place we can think about using prediction is in the area of detection. So detection is very important given any environment that we want to observe when something goes awry. We want to be able to know when unexpected changes happen. And one of those ways of doing that is through the use of anomaly detection. So anomaly detection is a very, very popular topic at the moment. And Wikipedia defines anomaly detection as the identification of observations which do not conform to an expected pattern. This is a very general, broad term. So we want to be really concrete what we mean by anomaly. So in this case, I like to call them blips and bloops. Very scientific. But really, they represent short-term anomalies and long-term anomalies. So in the short-term case on the left, we can see that we have some deviation of expected behavior for some period of time. And this period of time may be a few minutes, could be up to an hour maybe. And on the right-hand side, we see some deviation, but over a longer period of time. And this deviation may be over days, weeks, hours as well. But the fundamental thing to recognize here is that our two types here also contain periodicities. They contain trends and also cycles. So how might we be able to detect these two different types of anomalies, where we have a short-term or a long-term anomaly? Well, a natural starting place is to try and use something like static thresholds. So static thresholds are a great starting place if you know your data is relatively stable. In this case, we're looking at an example where we have CPU utilization. And we can see it's relatively stable. So we can use static thresholds, which are kind of a constant type of prediction, to say, have we exceeded some workload? However, can we use static thresholds to help find these short-term and long-term anomalies in our data that has cycles, periodicities, and trends? Well, it becomes very difficult. Where would we fit a static threshold in this case to find this short-term anomaly? So we have to use different techniques, but we can use the power of prediction, like we saw in the previous section, to help solve this problem. And there's a wealth of these different types of prediction algorithms, as we saw. So we have an FFT-based prediction that we use predictive scaling. But there's also other techniques, such as double exponential smoothing. This is a concept that we use a lot at Netflix, so much so that it's built into our primary telemetry system. But then there's other examples like Holt-Winters, which is an extension to double exponential smoothing, or ARIMA, which is a technique that has a funny name. So how do we actually go about doing this in our environment? So one way is we want to observe a set of metrics. These metrics could be system-level metrics. It could be application, performance-level metrics. So what we're going to do is we take that metric, we're going to compute our prediction. Maybe we use the fast-forward transform again, or maybe we use something else. But we're going to compute a prediction. Then from that prediction, we're going to compute the residual. And this residual is really the difference between our prediction and our actual. So what do we see right now? So you can consider it a delta. It's the residual. Then from that, we can set our static threshold all of a sudden. So let's walk through a real quick example of this. So here's an example where we're going to use the double exponential smoothing function to make a prediction. So here we see our original input line, which has a blip in it, or a short-term anomaly. And that's the blue line. Then we're going to compute our forecast, which is the red line that's using double exponential smoothing. So at each time step, we're going to compute a forecast. Then from that, we can compute our residual. So each time step, we're going to then compute the difference between our prediction and our actual. And this is what it looks like. So our anomaly becomes very evident all of a sudden. From this residual, we can then fit or set our constant prediction, or our static threshold in this case. And all is well in the world, and you can go home and not get woken up at 3 in the morning. However, you still have to pick this threshold. We're still trying to pick a static threshold for these signals. So we can leverage the power of statistics to help with this. For example, we can use very simple statistical methods to automatically find these anomalies in our residuals now. And a very common technique might be that of 3 sigma, or really 3 standard deviations. And there's a breadth of other techniques. So if you recall our initial workflow there, we were observing a metric, computing a prediction, taking the difference, the residual, and then putting a threshold. So a simple modification to this gets us some nice advantages. So instead of a threshold there, we're going to replace it with a statistical test such as 3 sigma. So we no longer have to set a threshold, and we can go off and set this loose on all 2 billion metrics. I don't think Roy will be too happy about that. But we can do better. Why use one algorithm when we can use multiple? So in this case, we could use 3 different detection techniques, or 3 different statistical tests. We could use, for example, our 3 sigma. We could use something called interquartile range, and so on. Then we have each of those different techniques vote, is there an anomaly or isn't there an anomaly right now? Then we want to combine those votes in some way. So a very simple way to combine those votes is majority. So do 2 of the 3 at least vote that there is something wrong. And this is what is classically referred to as an ensemble approach. We have gotten really good leverage out of using this in our production environment. We use a technique very similar to this to watch our KPIs. So as Roy mentioned, we have a KPI of stream starts per second, SPS. We use a technique very similar to this to watch our stream starts per second for any large deviations. Now, it's important to note there's also a breadth of other techniques out there and libraries that have been released by companies ranging from Netflix, Twitter, Yahoo, and Etsy. So I encourage you to go check these out if you're interested in the area of anomaly detection. So let's take a little bit of a look at a different detection problem now. Let's turn anomaly detection upside down. And let's look at something we call outlier detection. Now, we classify outlier detection to be the task of identifying unusual members from a set of generating mechanisms. Again, that is very broad, but it shouldn't be confused with the task of anomaly detection. So we have found that by breaking up the problems into anomaly and outlier, we get some very good mileage in that we're able to talk about the domains separately. And we'll see through an example what we mean by anomaly versus outlier. So in this case, let's talk about anomaly real quickly. So anomaly detection is the process of defining or trying to identify unusual events from a single member of a population over time. So that's our horizontal line here. So over time, we're going to look at one member of a population and try and find oddities. Outlier detection is the other way. Given a single point in time, we're going to look for unusual members. So there are many different ways or different areas we want to apply this type of technique of outlier detection. And one of those is in the area of server outlier detection. So for example, Netflix runs on thousands of servers. And of those thousands of servers, we typically see a small percentage of them become unhealthy. And this can relate to customer degradation. Furthermore, if we have our service owners trying to go find these, time can be wasted just paging through graphs. So we want a way to automatically find these servers that aren't behaving like each other. Now, just want to know that you don't have to have thousands of servers for this to be of use. You could have small deployments, medium, or large deployments, and the concepts still apply. You want to make sure that your services and applications are relatively performing as expected. So let's look at some examples of what we mean by outliers. So here's an example where we see a band of servers as reported by some metric. And we can see that we have a lone server that's trying to be unique and deviating away from the rest of the herd. In this case, this is what we refer to as outlier detection, or server outlier detection. We want to find that one server that is not behaving like the others. So this is a clean, easy example. So what about this case? Are there any outliers in this case? In this example, there actually are not any outliers. What we see here is that we can have metrics that start to band together. This could be because we have two different performance characteristics. For example, the top one might be one instance type, and the bottom might be a new instance type. So we want to be robust to these types of scenarios as well. So one way we can solve this problem of identifying servers that aren't really behaving like their peers is through the use of cluster analysis. Cluster analysis is an unsupervised machine learning technique. And conceptually, it defines that if a server belongs to a group, it should be near lots of other points as measured by some distance function. So things should group together. Now we have to make one assumption here. Our assumption is that servers that are running on the same hardware and software should relatively behave in a similar fashion. So there are a lot of different clustering algorithms out there. In our use case, we have found that the dbScan algorithm works extremely well. And dbScan stands for Density-Based Spatial Clustering of Applications with Noise. I'm not sure what came first, the name or the acronym. In this case, dbScan is going to iterate over a set of points, or servers in this case, and we're going to mark those servers in regions with many neighbors as clusters, and mark those in lower dimensional or lower regions as outliers. And this diagram depicts that quite nicely. So you can see we have three different high-density groups as identified by our three different colors. And those points that don't belong to any of these clusters that fall in these low-density regions are actually outliers. So built right into the algorithm, we have the concept of an outlier, and that is fantastic. So to use this in practice, it's very similar to our anomaly detection case. We're going to observe some metric. This could be system level, application level, run it through our dbScan algorithm. dbScan is going to return to us the set of servers that are outlying. We then want to perform some filtering, and this is where we can apply domain-specific logic. For example, let's say we don't want to actually do anything with outliers, servers that are, say, not taking traffic. So we are able to apply some domain-specific logic here. And then finally, we want to take some action. And there's a broad range of actions we can take. For example, we can send you an email. We can leverage the fact that we're in the cloud and terminate some of these instances. Or we can even say detach these instances from a load balancer so we can do some triage and maybe remediation. So we've seen here how we can use the power of unsupervised machine learning to be able to identify servers, part of our applications, that aren't behaving as expected. So I wanted to go into another use of outlier detection. It's a simpler use case and a little bit more concrete, and it's called automated canary analysis. So who here is familiar with the Canary release process? All right, we got some Berg enthusiasts. So for the uninitiated, the Canary release process is a deployment methodology where a new change to your application is gradually rolled out into production. As we do this gradual rollout, we're going to perform checks along the way. And we're going to perform these checks each time we gradually roll out our software. And at each of these checkpoints, we're going to make some decision as to whether or not we want to continue moving forward or if we want to roll back. So this process affords us some nice advantages. One of the advantages we're afforded is that we get a better degree of trust and safety in our deployments. As we're slowly rolling out our new software, we can perform these checks. And as we do those checks, we can get some better trust in our systems. We can also, based on that, get faster deployment cadence. We can deploy multiple canaries, all slowly rolling them out and making decisions as we go. And finally, we don't have to invest much into simulation engineering. Now, I want to point out that Canary analysis is not meant to replace any type of testing, whether it's functional testing, integration testing. It's meant to augment your deployment strategy or your deployment pipeline. So let's take an example, look at an example of what we mean by the Canary release process. So in this little example, we have some traffic. And that traffic is going through a load balancer. And we can see that that load balancer is splitting our traffic between two versions of our software. We got version 1 at the top there, which is currently in production, and version 1.1, which is our new Canary version. And we can see that traffic is split proportionately based on the number of servers we have. So as we go along and we keep turning the dial up and keep sending more and more traffic to our Canary version, we're going to do these checks. We're going to check, is it good? Are things looking good? Ideally, we get to a place where everything's looked good, and 100% of the traffic's now going to our new version. Now, one way you might want to do these checks is to look at dashboards. And as your metric volumes grow and you reach 2 billion metrics, building dashboards to do this type of thing just no longer works. So we need to come up with different ways to help automate this process for us. And one way we can do that is by, once again, leveraging the power of, say, statistics. So let's talk a little bit how we might automate this process. First, we need to identify a set of metrics that we want to actually analyze or compare. Again, these can be system-level metrics, application-level metrics, or performance-level metrics. We're then going to use a statistical test to try and identify the differences between our version 1 and our version 1.1, so our new and our old. And there's different ways we can do this. We could use something like a Mann-Whitney statistical test. Once we've identified the metrics that are different, we can then compute what we call a Canary score. Now, this Canary score indicates to us the overall similarity of our new software to our old software. And ideally, they should match 100%. So one way you can calculate this is as a percent of metrics that actually match. So in reality, our analysis workflow looks very similar to this. We're going to look at our set of metrics again. We're going to perform that statistical test, identifying the metrics that are different between our Canary and our production. We're then going to calculate that score, ideally getting 100%. Once we have that score, we're going to make some decision. And that decision is going to indicate to us, should we continue going forward with our rollout, or should we move back? Now, this technique has been extremely useful for Netflix, so much so that it's been built into our continuous delivery pipeline, Spinnaker. But we've had to make some changes to this, the way we do this analysis. So we've augmented it. So in this case, we're actually adding a little bit of complexity, but it's the complexity in the sense of we're adding a control group right in the middle. Now, this control group, if you note, is the exact same version as the previous version, it's version 1. But you'll notice it's sized the same size as our Canary version, so it's 6 servers. By doing this and introducing the concept of a control group, we can get an apples-to-apples comparison. So we can now compare our metrics from the Canary to our metrics from a control, and we're going to do an actual apples-to-apples comparison. Something else this affords us is the ability to start the two groups up at the same time and monitor their startup characteristics. And then finally, we've augmented our workflow by adding on our automated analysis on the end of our pipeline. And this ties into our primary telemetry system. So it's one thing to automatically generate the score and to decide if we want to move forward or move back with our deployments, but sometimes you need manual intervention. So instead of giving our developers and service owners dashboards to look at, we're able to generate a report. And this is a curated Canary report. So in this report, we can see we have that score. We have that high-level Canary score. And this one scored 92.3%. So our service owners can use this to help triage and dig into why did their new software, their new deployment, not actually match in performance to the existing software. So over the last couple of minutes here, we've looked at different ways we can go about using, say, machine learning statistics to monitor our environment and to help make some automated decisions for us. So So moving forward, and the path ahead of us, we want to be able to use and leverage the power of correlation. So everything we've looked at so far is looking at an application or service level itself. So we're looking in isolation. So we're analyzing each individual service themselves. However, we work in a microservice architecture. So at Netflix, we have over 700 microservices. And this diagram is what we call the Death Star. This represents the interactions between all of our services. So this is a real diagram. It's been anonymized, but we can see that there's some services that are heavily interconnected with other services. So all of our current detection techniques have been looking at a service-by-service level, but we know there's interactions between all these services. So we want to be able to leverage the power of correlation analysis to be able to discover some of those interesting correlations or dependencies and help make us better informed decisions about our environment. So let's look at a little bit more of a concrete example of how we're thinking about doing this. So in this case, we have a dependency graph where we have a set of services and their dependents. So for example, the node A here represents some service A, and it has some dependencies B and C. Now let's say we're running these detection techniques that we have, and we all of a sudden notice we have a spike in alarms on 3 of our services, say service J, E, and H. So we may alarm our service owners at each of these tiers and say, hey, your application is a little wonky right now. However, we can see that there's a common dependent here. We've got a common dependent on F. And so why didn't F fire? Well, maybe F here doesn't have any alarms or doesn't have any telemetry around it. So we want to be able to use the power of correlation analysis to be able to look at our environment from a macro level and say, well, J, E, and H all have a common dependence. F, is it actually encountering any issues? And there's another case where we want to use correlation analysis, and that is in the case where we're looking at a single service itself, and we want to be able to correlate metrics. So what I mean by this is, let's say that we have an alarm set up on our CPU. So let's say we set up a static threshold, and it triggers an alarm. There's an increase in CPU. We can then go and correlate that potentially with other metrics in our environment. So for example, we can maybe correlate that with a spike in our HTTP 400s. At the same time, it may be inversely correlated with HTTP requests, or maybe the input into our service. And if I recall, Roy, this was actually a real case example, or a real example.
Sorry. Yeah, actually, this was a funny one. We had a service that had a CPU spike and fired some alarms. And then when we looked, because our system was able to use, is it Pearson? A Pearson algorithm to tell us what other metrics were changing in about the same sort of direction as CPU, we saw an increase in 400s and a decrease in requests, which is kind of weird if you think about it. It turned out that the service had a 400 handler that was a CGI script written in Perl and was remarkably non-performant because it was doing really complex stuff. So as soon as some people started hitting an unallowed endpoint and generated a bunch of 400s, performance dropped through the floor while CPU spiked. And it was really interesting to actually look at how these 3 graphs were very tightly correlated.
So this is an example, again, where we can potentially leverage the power of correlation analysis. Something to note is, in an environment where we have powerful correlation methods, we don't have to set up alarms on all of our metrics. For example, let's say we just set up an alarm or an alert on our CPU. We can then use correlation analysis to go through and find other metrics that are very similarly correlated. And then finally, there's another use case where we want to start investigating the use of correlation analysis. So imagine that you care about this metric. Let's say this is a KPI. So we can see that it has some interesting characteristics. And let's say that we use correlation analysis and we find out that it is strongly correlated with this metric. So do we actually care about these metrics? Are we able to use correlation analysis to say, well, we should more or less be interested in the left one, or maybe we're more interested in the right one? Or actually, maybe there's a parent metric that we should be really watching. So we're thinking about how we can use correlation analysis to help prune the space of metrics that our users have to explore through and do that in an automated fashion. And the whole idea here is to reduce the cognitive workload of our service owners and engineers to figure out which metrics from our 2 billion are interesting and meaningful for them.
Shall I? Alrighty, so what's the whole takeaway here? Well, I'm hoping that if we've done our job right, algorithms like DES or IQR or FFT or DBScan are a little less mysterious and magical. For what it's worth, speaking not as a data scientist, the Wikipedia article, for example, on DBScan is so readable, even I could read it and understand it. And that's a very, very high bar. And we think that if you have a reasonable telemetry platform, you can actually start experimenting with these algorithms and approaches by basically not trying to build it into your telemetry platform necessarily, but really have a standalone component that simply talks to both your telemetry platform and to your orchestration system to do some interesting things in your environment. So I started off saying that our goal was to help people figure out how they might find some relevant use cases here and some relevant algorithms they can start working with. And I'm interested in testing the hypothesis that this was potentially going to be useful. Show of hands, did anybody here find something here that they're interested in actually experimenting with when they go back to work? Hey, awesome. So we're successful. This was a brief survey. We didn't go in deeply into a lot of data science and algorithms. We're happy to have those conversations. At least Chris is. I'm totally ignorant. We're also happy to have conversations about different use cases for these kind of things in cloud-based ecosystems. We've talked about a few of our use cases. As you find other use cases, frankly, we'd love to know about them. So with that in mind, we're going to publish this presentation sometime today and tweet about it. It includes a bunch of links to much more detailed information, including some Netflix presentations. Remember to complete your evaluations. This is Chris. These are Chris's and mine Twitter handles. Feel free to tweet us with any interesting use cases you can come up with. And I believe we have 11 minutes and 56 seconds for questions. What can we tell you?